Hello, everybody. How are you all doing? I hope you all are doing fine and you all are safe. Welcome to the channel and welcome back to the playlist in which we are discussing the mathematical operations of on different type of signals and systems. So up until now, we have seen different kind of operations which takes place on signals. We have seen addition, subtraction, multiplication, and division. We have also seen operations like integration and differentiation. After that, we saw a series in parallel connection of systems. We saw the reliability calculations and system reliability. System reliability. Apologies, guys. Then we saw cascaded systems, and after that, we saw uh, LTI systems. What is an LTI system, and what kind of operations which takes place on it. For continuous time signals, we saw impulse response characterization and convolution integral, and today we are going to see impulse response characterization and convolution sum, which will be of course for discrete time signals. We also visited convolution and its properties, its different kind of properties. We also saw LTI system response and properties for impulse response. In that we saw stability or dynamicity of my system. We saw the static either my system is a static or dynamic system. We saw the causality property, and also we saw the step response. So today, all that we have seen up till now was in regard of continuous time signal. Today what we are going to discuss will be in regard of discrete time signal, and from today onwards for few lectures we will be discussing about the discrete time systems only. After that, uh, another point that I wanted to discuss that if you have seen the continuous times impulse response and characterization and convolution integral, which was for a continuous time signal, uh, then it would be a lot easier for you to understand this concept and if you're already familiar with convolution, if you're following the lecture series from the beginning, it would be very easy for you. But if you're not, then you encourage you all to go through that all the videos which you have been produced earlier. So in continuation of previous videos, the impulse response characterization and convolution integral, which was for continuous time signal. Today we are going to discuss about the impulse response characterization and convolution sum, which is for discrete time signal. So if you haven't seen the previous video, check it out. The link will be flashing on the I button on the top right hand side corner of your screen. So just click on it and you can find it. Now let's move forward with the impulse response characterization for my DT system. So if you are following my videos, you already have some idea about impulse, what is an impulse, and what is a discrete time system. Also, if you don't have idea about LTI systems, you can check out the last video as well, in which we have discussed about what is an LTI system. Now coming towards the convolution, not convolution, discrete time signal as a weighted sum first. So what happens now, what my convolution sum or a linear convolution does, it relates my input, output, and my unit sample response of my my discrete time systems. Okay, so uh, let's take a signal, and let's take the signal, let's call it x of n, and represent it this way: 2 1 3 minus 2 and 1, and 3 is at 0. Okay, now as you can see here, the value of x at if this is 0, that means this is -1 and this is -2. If this is 0, this means this is 1 and this is 2. So this means at x of n is equals to -2, the value of my signal is 2. At x of n is equals to -1, value of my signal is 1. At x of 0, value is 3, and x of 1 value is -2, and at x of 2 value is 1. And we have represented that signal here in this image, as you can see, right? 2, 1, 3, -2, and 1, as you can see, from -2 to 2. Now we all know what is an impulse signal, right? For on for value of n is equals to 0, it will have value 1, and everywhere except it will have value 0. Okay. Now, but if I tell you I want to delay this impulse function by some value k, okay, by some k samples, then how will I represent my impulse signal? I will be representing my impulse signal like this: delta n minus k is equals to 1 for all the values of n is equals to k, and k will be only, there will be only one value of x of n is equals to k, and will be 0 for all the n's does not equals to k. Okay, so that is how we represent my delta n minus k. Now I have represented that signal here in image B, and here what did I do? I took the value of k is equals to 2. So at k is equals to 2, the value of my delta n minus k is 1, because what is it? It is an impulse signal, right? Now if I take the product of x of n into del n minus k, we can express it with the help of impulse function property, right? So what I did here, I have taken the multiplication of x of n and del of n minus k. So it will be x of k into del of n minus k, right? Because if you remember, in the first lecture series of basics of signals and system, we discussed about the properties of impulse signal, and in that we have discussed how x of n into del of n minus k can also be written as x of k into del of n minus k, because eventually you will get the same result. So what will happen, let's come here. We took x of n, which is given here. We took del of n minus k, which is given here. And what did we do? We took simply, we multiplied them, as this operation is a multiplication operation. So at -2, we are having axis value 2, but value of del of n minus k is 0 at -2, so multiplication will be 0. Same thing will happen at -1. X of n is having value 1, del of n minus k is having value 0, so we will put 0 again here. Then for x of 0, we are having value 3, but here see, at x of 0 again we are having value 0, right? Why? Because it is impulse, but it is delayed impulse, so we will not have any value of value at 0, so again 0. Same will happen with 1 as well, and same will happen at 3 as well. But for the value of 2, because we have taken k's value is equal to 2, so x's value at 2 is 1, k's value is 2 is 1, so 1 into 1 will be equal to 1. So my resultant signal will have value 1 at n is equals to 2. So that's what we have done. That's what we have done. Now let's take do one operation, very interesting operation. Let's take the value of n is equals to sorry, not n. Let's take value of k is equals to minus 2 till 2 and try to find out this multiplication, right? So let's try to find out the value of this multiplication. So what we will do, we will take again here k is equals to minus 2 we have taken, and at k is equals to minus 2 what we have done, uh, we are taking multiplication. So see here, what was the value of x of n at minus 2? It was 2. So only for that value, because we are taking k is equals to minus 2, so for only that value we will get result. And what it will be, what the result will be, it will be same as the value of x of n or x of k, sorry, x of n at n is equals to minus 2. What was the value? Minus 2. At minus 2 we were having value 2, so the result will be at minus 2 we will have value 2. Same operation we will do again. This time k will be minus 1, so we will have minus 1 here, and value of my n at uh, value of x of n at n is equals to minus 1 is 1. So minus 1 into 1 will be again, sorry, 1 into 1 is again will be 1. Again at 0 same thing will happen. Here we are having 3, and again again my value at del of n minus k is 1, sorry, k is equal, at k is equals to 0, my value of k is my value of del k is equal to 1. So multiplication will be 3, and same ways we can find out for n is equals to 1 and n is equals to 2. We can find out at n is equals to 1 we are having getting value minus 2, and n is equals to 2 we are getting value 2. So when we are watching them in a vacuum, when we are watching them separately, everything we are getting is an impulse. See, here I'm getting impulse, here I'm getting impulse, here I'm getting impulse, here again we are getting impulse, here again we are getting impulse. But when we take summation of that impulse, what will happen? So what will happen, we will get my original signal return, we will get x of n back. See, at minus 2 we are having value 2, at minus 1 we are having value 1, at 0 we are having value 3, at 1 we are having value minus 2, and at 2 we are having value 1. See this signal and try to match it with my original signal, this one, at x of n, this my x of n, right? We are having 2 1 3 3 minus 2 and 1, again 2 1 3 minus 2 and 1. So what we did, what did we do? We did nothing, we simply added them. We simply take the addition, summation of them at k is equals to minus infinite to infinite x of k into del of n minus k. And by the way, if you remember the convolution property which we saw for the continuous time signal only, so this is convolution sum, this is nothing but convolution sum, and it can be given as using this formula. And if you are following lecture series since the beginning, now you might have noticed what is the difference between the convolution integral, which was for continuous time signal, and convolution sum, which is for my discrete time signal, right? So in that we had what did we had, we had integration sign. We were integrating my samples as it was a continuous signal. Here we are having samples at a certain frequency, at certain after certain time we are taking samples. So what we are doing, we are adding all those samples and we are getting x of n. So that was your dt dt signal as a weighted impulse or a weighted sum of impulse. Now let's come to the convolution sum formula, and you already seen what is the formula for a convolution sum. It is x of as you can see here, x of n is equals to k is equals to minus infinite to infinite x of k into del of n minus k. So how did we got to that formula? Let's try to figure it out. Let's try to see how did we found that formula. So let's consider again x of n, and if I apply my x of n as an input to a dt system, and I get response y of n is equals y of n of the system, and I represent it in such manner as you can see in the step 1 here. Y of n is equals to t into x of n. And now putting this x of n in the above equation, this very equation of y of n, we will what we will get? We will get this formula: y of n is equals to t, k is equals to minus infinite to infinite x of k into del of n minus k. Now as this is a summation sign, we can also write this formula as a sum for different values of k, right? So let's try to write it as a sum of different values of k. So at k is equals to minus 3, we will get x of minus 3 del n plus 3, right? Because minus minus will be plus. Same for k's value of minus 2, we will get x of minus 2 del of n plus 2. Again same ways for k is equals to minus 1, we will get x of minus 1 del of n plus 1. At k is equals to 0, we will get x of 0 plus del of n. K is equals to 1, we will get x of 1 del of n minus 1. K is equals to 2, we will get x of 2 del of n minus 2, and so on, right? And we also know that this system which I'm talking about is actually a linear system, right? Why? How do I know it? Because that's what this system is about. Like, this is a LTI system we are talking about, right? And if I'm talking about an LTI system, which means it is linear time invariant system. So of course it is linear system to begin with. So as it is a linear system, what I can do, I can multiply my t inside, because remember the linearity operation, right? You can put what is out of the bracket inside the bracket, and then you can multiply it with if it is in multiplication, you can multiply it. If it is division, then you can divide it. So we will take t inside, so it will be t into x of at k is equals to minus 3, we will have t into x of minus 3 del n plus 3. At k is equals to minus 2, we will have t into x of minus 2 del n plus 2, and so on, similar ways. I think you got the point, right? Now as you come here and see this equation which we have just derived in the step 3, we are taking values of k is equals to minus 3, minus 2, minus 1, 0, 1, 2, all those values, right? So what we are doing basically is we are taking the values of k as constant values. And if you remember the scaling property of linear system, we can do one thing. We can also write it this way, as it is as all three of these terms, t, x of minus 3, and del of n plus 3, all of them are in multiplication. So what we will do, we will keep this x of minus 3 out, and we will multiply t into del of n plus 3. Same ways we will keep x of minus 2 out, and we will multiply t with del of n plus 2. Same ways we will take x of minus 1 out, and t is equals to okay, so we will take t into del n plus 1, and same ways till further, right? So after doing that, we can also write my formula this way. I can take summation k is equals to minus infinite to infinite x of k, and then we took multiplication of t into delta, so we are putting t into delta, n minus k. So what will formula become? Formula will become summation k is equals to minus infinite to infinite x of k into t or t into delta n minus k. So what will happen? The response of this system to unit sample sequences can also be given as t into delta n, can also be written as h, right? And as we are writing t into delta n is equals to h of n, let's put a delay to it. Let's put a delay to k, and we will get t into delta n minus k is equals to h of n minus k. And now let's put the delay which we took into the main equation, original equation, summation equation, right? So what I will get? I will get y of n is equals to summation of k is equals to minus infinite to infinite x of k into h of n minus k. So when you see this formula, what is it? It is nothing but the formula which we saw in the previous slide as well. And this formula is the formula for convolution sum. So basically what we are doing, we are doing the convolution between these two signals, x of n and h of n, h of n minus k, right? So this equation is giving the response of LTI system to your input. And uh, the equation is called convolution sum equation. Now as we know that the convolution is a commutative operation, right? We have seen in the previous videos as well. We have even proved the properties of convolution for CT system, right? So it has some operations, four operations in particular, and four operations can be very helpful to us while doing various calculations. The first one is called folding operation. In what do we do? Think of your signal plane as paper, a piece of paper. So what do we do? Uh, we fold the system h of k at t is equals to 0. Uh, so what happens? We can get the value of h of minus k, right? You have a system which is initiating from 0 and it is going towards infinity. And if you want to find the same signal but in negative, you want to find the h of minus k. So what you will do? You will simply fold your sequence from k is equals to 0. So that is your called folding property or folding operation. Second operation is called shifting operation. What happens is shifting is uh, we simply shift my signal by some delay, right? We let's say initially we did the folding, so we got, instead of h of k, we got h of minus k, right? So now what we will do? We will take this h of minus k and we will shift it depending on the value of my n and y of n. We will shift it, right? So this is a pretty much basic shifting which we did when we were learning time invariant and time variant systems. So we can simply shift it. Third one is the multiplication. And what happens in multiplication? That simply we take the multiplication of x of k and h of n minus k, and we do the multiplication of both of them. So basically it is convolution, nothing but convolution. And the fourth one is called summation, which we did just few minutes ago. That the product sequence we obtained by the multiplication of x of k and h of n minus k, and we added them all over with the values of k, different values of k, to find my resultant signal, which was y of n for our case, right? Now let's solve an example to understand this signals, this operations better way. So see what is the question. We have to calculate the linear convolution of this my x of n and h of n. The value of x of n is equals to 1 1 1 1, and the value of h of n is equals to 2 2. Okay, and we have to do the calculation graphically. So let's try to let's first draw this x of k and h of minus k, or h of k. So x of k is simple signal which is initiating from 0 and is having value 1, and it is going, how far is it going? See, 0 1 2 3, it is going till 3. So we will write at 0 1 2 and 3 we will represent my signal x of k. Now for h of n, uh, because we have to find the value of n minus k, we are not finding the value of k only, we have to find the value of n minus k, which means you need minus k in your convolution integral, right? So we what do we have to do? Folding. See, we have to fold my signal. So I will consider this 2 2 as I will fold it on the x-axis, and what I will get, I will get value 2 at as equal x is equal at k is equals to 0, and I will get the value 2 at k is equals to minus 1. As what did we do? We had folded my original signal, and we, what did we got as an output? We got h of minus k here, right? And now let's do the multiplication operation, because we have to find the convolution, right? That's what we need to do. So when we multiply them, see, for value of uh, uh, at k is equals to minus 1, what value my x of k has? It has nothing, it has 0. So, and what value my h of minus k is having? It is having minus 1. So minus 1 into 0, sorry, minus 2, sorry, it is having minus 2, not minus 1. So minus 2 into 0 here will be 0. Then for k is equals to 0, x of k is having value 1, and h of minus k is having value minus 2. So 1 into 2, sorry, not minus 2, it is having 2. See, plus 2 it is. Its value is plus 2. If it is if it was indicating downwards, then it will be minus 1. It is not minus 1, it is plus 2. See here, we are having value plus 2. So 1 into 2 will have value 2. Then at k is equals to 1, x of k is having value 1, and k is equals to 1, h of minus k is having value 0. So 1 into 0 is again 0. Same ways at x of k is equals to 2, sorry, at k is equals to 2, x of k is having again value 1, and again k equal to 2, h of minus k is having value 0. So again 1 into 0 will be 0, and same ways 1 into 0 will be 0 for k is equals to 3 as well. So when we add them together, we took summation operation. So what we will get? We will get y of 0, right? Y of 0, because my signal was starting from 0, and it will what it will be? It will be 2, because when we added them, the only value we got was 2, right? So initially we got the value 2. First we took n is equals to 0. Now let's take n is equals to 1 and try to calculate again. So when we took n is equals to 1, I was getting value again, x of k will remain same. Same ways my h of k will become 1 minus k, right? See the formula, right? X of k, h of n minus k. So x of k will remain as it is, n is equals to 1, so h will become h of n minus k, which means h of 1 minus k. So basically when we wrote h of 1 minus k, we basically delayed our signal by 1. So what will happen? This value of k is equals to, at minus 1, what value my h of minus k holding? It was holding 2. So it will shift one step here, it will shift one sample on the right, and this value at k is equals to 0, h of minus k was 2. So this value will also shift one value right. So what we will get? We will get something like that. k at k is equals to 0, my h of 1 minus k will become 2, and k is equals to 1, h of 1 minus k will become 2, right? So basically I'm having the same signal, but it is shifted to the right a little. And we again will do the multiplication, and again by doing the multiplication, what we will get the value of uh, y of n. For y of n, by doing multiplication, we will get the value for only k is equals to 0 and k is equals to 1, because except for that, all the values are zeros, right? So we'll get again 2 into 1 is equals to 2, plus 2 into 1 is equals to 2. So 2 plus 2 will be 4, so y of 1 will be 4. Same way as we will do the operation for n is equals to 2, when we take n is equals to 2. So again this was 1 minus k, so this time h of 1 minus k will become h of 2 minus k, because n is equals to 2. And as we are taking h of 2 minus k, which means it will shift one more signal to the right. It will move one more sample to the right, not signal, it will move one more sample to the right. So what we will get here again, for value of 1 we will have value 2, and as it is shifted towards the right, so this value will come here and this value will become at 2. So we will have uh, at k is equals to 1 we will have value 2, and k equal to 2 we will have value 2. And again doing multiplication, we will get 2 into 1 is equals to 2, 2 into 1 is equals to 2. My x of k is remaining as it was in the beginning, there is no change in x of k. So uh, again 2 plus 2 will become 4, and y of 2's value will be 4. Same way as for n is equals to 3, again my signal will shift one more sample to the right, and again we will take the multiplication, and again we will get the value 4, right? You get the drill, what is going on right here, right? So that was for n is equals to 3, and again we will do the same thing for n is equals to 4. But this time, see, as we are taking n is equals to 4, that uh, my x of n is only going till k is equals to 3. There is no value at k is equals to 4. So at k is equals to 4, my x of k is equals to 0, but h of 4 minus k will have value 2. So 2 into 0 will become 0 here. All these signals will already are 0. All these signals are already 0, and at k is equals to 3, my x of k is 1, and h of 4 minus k is having value 2. So 2 into 1 will become 2, and all the rest will be 0. Now how would you know how far you have to go? Like you have taken n is equals to 4, then n is equals to 5, then n is equals to 6. How far do you have to go? So for that we have a formula. If there are m samples in x of n and n samples in h of n, then what you will do, you will take the number of samples in y of n, and how much they will be, it will be m plus n minus 1. So how much it will be, what is your m, how many samples did you had in x of k? You had 1 2 3 4 samples. So 4. And how many samples did you had in h of k? You had 1 and 2 samples. So you have to do 4 plus 2 minus 1, which means you have to go 4 plus 2 is equals to 6, minus 1 is equals to, total you must have 5 values for your y of n or your output signal. So again, see, did we took the 5 values in the beginning? We took n is equals to 0, then we did for n is equals to 1 2 3 and 4. So including 0, we did for 5 values of n, and we obtained the value of y for 5 values of n. And that's how far we will go, because m plus n minus 1, which means what is value of m, it is a number of signals h of k is having. So 1 2 3 4 it is having, number of samples x of k having, sorry, 1 2 3 4 it is having. So m will be 4, number of samples h of k is having 1 and 2, which means 4 plus 2 is equals to 6, minus 1 is equals to 5. So you must have total 5 numbers, and including 0 1 2 3 and 4 we have calculated for 5 samples. So we will stop here, and we will give y of n is equals to 2 4 4 4 2. That is your final output, that is your final output signal, right? So I hope now you might be clear about the folding, shifting, multiplication, and summation operation. If you still have any doubts, you can mention your doubts in the comment section below. You have any other queries or any other thing you want to talk about, you can feel you are free to drop your thoughts down in the comment section below. If you have any feedbacks are most welcome, guys. You can mention your feedbacks in the comment section below as well. So I will be seeing you in the next lecture. Until then, thank you very much for listening. Goodbye.